Hello everyone. Last lecture we discussed the liquid drop model where we derived an expression for the mass of a nucleus using the phenomenon of a liquid drop and considering the Coulombic energy and the asymmetry between neutrons and protons. This semi-empirical mass formula, we also discussed that it can predict the masses of nuclei quite accurately. Today I will discuss the other applications of liquid drop model. One of the most important applications of liquid drop model is to predict the energetics of beta decay in an isobaric chain. We know that beta minus decay occurs in an isobaric chain when and in this process the atomic number is increased by 1, while in beta plus decay the atomic number decreases by 1. Now let us try to calculate the Q beta for beta decay, and then we will see the systematics of the Q beta decay. So for beta decay, let us calculate, we can in fact write the mass of a nucleus in terms of the coefficients of Z and Z square. So the mass of a nucleus or an atom mZa can be written as mass of Z protons, mass of A minus Z neutrons minus the binding energy term. So this we have already seen, that there is the semi-empirical mass formula. And now let us try to rearrange these terms in terms of, we'll try to get this formula in terms of Z independent term, Z dependent and Z square dependent terms from this above form. So you can write this as, so you can, let us see, you can say Z mH plus AMN minus ZMN minus AVA plus AS e to the power 2/3 plus AC its square upon e to the power 1/3 plus, you can open this square, so it will become AA, and A square upon A will become A plus 4AA, and it will be, so it will be 2 square 4AA Z square and minus 4AA this is upon A, and it will be 4AA A. 4AA upon A, it will get cancelled out, plus minus left. So now let us try to rearrange the terms which are independent of A. So that will be AMN minus AVA plus AS e to the power 2/3 plus AAA. These are the terms which are independent of Z. So that becomes the alpha. So you can take A outside and say alpha A. Then we will have the Z dependent term plus MHZ minus MNZ, and then you will have here a term minus 4AA ZA. ZA, it will be minus 4AA AZ. So these are the Z dependent terms. So you can take out Z, and in fact you will have here also delta also. And then lastly you will have the term which are depending upon the Z square. AC Z square upon e to the power 1/3 plus 4AA Z square by A. So these are the Z square. So you have actually tried to rearrange this formula in terms of coefficients of A, Z and Z square. That is the purpose of rearranging this mass formula. And then you can write in terms of alpha A plus beta Z plus gamma Z square plus minus Z. These are the terms, and you can rearrange them so that this the equation looks familiar to you in terms of the coefficients of Z. Now, this alpha, beta, and gamma actually are called the local constants because they are constant for that particular isobaric chain because they depend upon the mass number. And if you want to find out the most stable isobar in this isobaric chain, then you can differentiate this formula with respect to Z, and so you get, so from here you get beta plus 2 gamma Z. Delta m by delta 0, delta z equal to beta plus 2 gamma z. And if you equate this to 0 to get z0, then it becomes beta plus 2 gamma z0 equal to 0 or beta equal to minus 2 gamma z0. So essentially you have beta equal to minus 2 gamma z0. So you will have gamma and z0. These are the two local constants. If you know the gamma and z0, then you can find out the Q beta for the particular isobaric chain. So that we will discuss in the next slide. So now let us discuss the isobaric chains for a particular mass number wherein the beta plus and beta minus decay is going to take place. So we just discussed that the mass can be written in terms of alpha A plus beta Z minus plus gamma Z square plus minus delta, and the beta can be replaced by minus 2 gamma Z0. Okay, so I have put here minus 2 gamma Z0 into Z plus gamma Z square. Now, as we discussed that for the minimum mass, the nucleus is most stable. So we can write the mass of the most stable isobar by replacing Z by Z0. So it will become alpha A minus 2 gamma Z0 square plus gamma Z square 0 square plus delta. So it will becomes alpha A minus gamma Z0 square and plus minus delta. So now let us see for odd A isobaric chain where delta equal to 0. So for the moment we will forget about delta term because for odd A delta is equal to 0. So let us try to find out the mass difference mz comma A minus mz0 comma A equal to, so you subtract from here, it will be alpha A minus 2 gamma Z0 Z plus gamma Z0 Z square minus alpha A plus gamma Z0 square. So you see here alpha A will cancel out and it will become, you see here gamma is out. What we have is Z square plus Z0 square minus 2 gamma Z0 Z. Which is nothing but gamma Z minus Z0 square. Now you see here the delta M, the mass difference between any isobar and the most stable isobar follows a parabolic relationship. So we can write this in terms of, if you plot this, then we get delta M versus Z as a parabola where minimum corresponds to Z0. Now this delta M is nothing but Q beta or isobaric chains. So now you can see here that this is what we mean by the mass parabola. The masses of the isobars of a beta decay chain fall on a isobaric and on a parabola. Now you see here as the Z is increasing from left to right, you will see that the up to Z0, the lower lighter Z values will undergo beta minus. The heavier Z values will undergo beta plus. So irrespective of where you produce, for example, if you produce a fission fragment, it will be having highly neutron rich, so it will undergo beta minus decay to ultimately lead to stability. If you produce a highly neutron deficient nucleus, it will undergo beta plus decay or electron capture and come to the rest at Z stable. So this is what we mean by the mass parabola, and using this we can find out, from this formula you can find out the systematics of beta decay. So let us see, for a odd A isobaric chain, how we can derive the Q beta. So let us write now, this is a typical example of a isobaric chain for odd A. So you have one stable isobar shown in black, and the ones on the left hand side are undergoing beta minus decay, and the ones on the right hand side are undergoing beta plus decay to reach the stability. And so this can be written, this can be shown as a mass parabola. This is Z0, this is delta M or Q beta. Now let us try to derive expression for the Q beta from this graph. So we write MZA equal to, so what did we write? Alpha A minus 2 gamma Z0 Z plus gamma Z square. And now you have the next isobar Z plus 1 comma A equal to alpha A minus 2 gamma Z Z plus 1 plus gamma Z plus 1 square. So this is what is the delta M value for adjacent isobars. That means you are not trying to find out the Q beta for a beta decay. So it will get cancelled out. So what we have is delta M equal to minus 2 gamma Z0 Z plus gamma Z square plus 2 gamma Z0 Z0 Z plus, it will be minus, it will be plus 2 gamma Z0 plus gamma Z plus gamma plus 2 gamma Z. So this is, since it is a negative sign, it will become minus minus minus, because Z plus 1 square, these are the two terms. So now we can find out delta M equal to, so it will be cancelling out here. You see here, gamma Z square will cancel with gamma Z square here. So it will cancel out gamma Z square. And so we are left with minus 2 gamma Z2, this also will get cancelled out. So we will have these three terms. It will be 2 gamma Z0 minus 2 gamma Z minus gamma. So it will be 2 gamma, you can take out Z0 minus Z minus half. This is the relationship for the Q beta minus. So we showed Q beta minus because we are going from Z to Z plus 1. Similarly, you can do an exercise. So this is for beta minus decay, Q beta minus equal to this. To do the same exercise for beta plus, then Q beta plus will be MZA minus MZ minus 1 comma A. And this Z minus A, so now you can again do the same exercise and you will find this becomes equal to 2 gamma Z minus Z0 minus half. So using these expressions, you can find out the Q beta using the local constant gamma and Z0. So what essentially you need is, you need two Q beta values along this decay, this parabola. If you know the two Q beta values, then you can find out the local constants Z0 and gamma, and thereby the beta value of any other isobaric chain. So this is the application of liquid drop model. So let us now discuss the Q beta systematics for even a isobaric chain, and an example of that is given here. That is this copper 64, iron 64 decaying to cobalt 64, decaying to nickel 64, by beta minus, and then we have from germanium 64 to gallium 64, beta plus to zinc 64. And as you can see here, there are two stable isobars in this particular isobaric chain. That is very common for the even A isobaric chain. So we have already discussed for the odd A isobaric chains, that is the delta M for beta decay will be gamma Z minus Z0 square. That we have seen for the case of odd A isobaric chain. Now in the case of even A isobaric chain, there can be two situations. That is, you can have odd nucleus to even nucleus, and if this happens, then there will be a term 2 delta for odd to even beta decay, and it can have even to odd, then there the term will be minus delta, so it will be gamma Z minus Z0 square minus 2 delta for even to odd. So what essentially you have is that you have, if you see the mass parabola for even A isobars, then you will have two parabola, one for this even and one for odd nuclei. And so the beta decay will take place. So this is the Z0 from even to odd to even to odd, and like that. Similarly, here you will have this way, and so finally you may end up with two stable isobars, and this can undergo probably beta plus beta minus, like in the case of copper sheet. So in case of even A isobaric chain, you have two parabola because of the pairing the difference. So odd isobars lie on the upper parabola, and the even isobars lie on the lower parabola. So let us now calculate the Q beta for the isobaric chain. So for beta minus decay, we have already seen the Q beta equal to, for our odd A isobaric chain, it was Z0 minus Z minus half 2 gamma. So if it is odd to even, then it will be plus 2 delta. And if it is even to odd, then it will be 2 gamma Z0 minus Z minus half minus 2 delta. So that is the only difference in terms of for the odd A to even A isobaric chains. Similarly, for beta plus decay, Q beta will be 2 gamma Z minus Z0 minus half plus 2 delta for odd to even, and Q beta plus equal to 2 gamma Z minus Z0 minus half minus 2 delta for even to odd. So this is how you can write the Q beta in terms of the local constants gamma and Z0. And if you know the Q beta values for two decays in an isobaric chain, then you can calculate gamma and Z0, and thereby you can calculate the Q beta for any other decay in the isobaric chain. So this I have tried to show here in this graph. You can see here, this is a isobaric chain for mass number 156, and you can see here from neodymium, promethium, samarium, europium, gadolinium. So you can see the two parabola, and there is a change from, there is a beta decay from odd to even. So promethium to samarium, samarium to europium, europium to gadolinium. And here again you have from erbium to holmium, holmium to dysprosium, and terbium to dysprosium. So you see here that even a isobaric chain can have more than one stable isobar. This is a corollary of the two parabolas. So you can there can be more than two stable isobars for a even isobaric chain. So this is the application of liquid drop model. Just to do again see how we can use this problem. We solve a problem here for mass number 141. The beta values, Q beta decay value for the promethium 161 to neodymium 141 are is given here, and for neodymium to praseodymium the beta values are given. We have to calculate the Z0, the most stable isobar, from the information that is given here. So we can write the expression for Q beta plus 2 gamma Z minus Z0 minus half. So Q beta is 3.72. So you can write 2 gamma 61 minus Z minus 0.5 equal to 3.72. So you can write this expression. For the other beta decay, beta plus decay, 2 gamma 60 minus Z0 minus 0.5 equal to 1.82. So these two equations are there, and you can solve them for Z0 and gamma. And by solving, you will find gamma is 0.95 and Z0 is 58.55. So that is close to 59. So 59 is the praseodymium. So praseodymium is the most stable isobar of this isobar chain. So this is how we can use the systematics of beta decay and the liquid drop mass formulae derived to find out the Q beta value for beta. Now let us see how the liquid drop model can explain the energetics of nuclear fission process. We know from the binding energy data, binding energy curve, that is binding energy as a function of mass number. The binding energy per nucleon reaches a maximum about mass number 60, and so heavy nuclei, when they split into two equal fragments, there is a gain in binding energy, and so binding energy, the Q value should be positive. Like the light nuclei, when they fuse together to form a heavy nuclei, there is a gain in binding energy, and so these are in the exoergic reactions. So grossly, you can say that heavy nucleus can undergo fission, and because of the change in binding energy from low binding energy to high binding energy. Let us now calculate the Q value for fission from the liquid drop model. So in assuming that the liquid drop model, it is considered the highest energy release for a symmetric splitting of a heavy nucleus, we will consider the splitting of the heavy nucleus AX into two equal halves. So we will say Z going to Z by 2, A going to A by 2. So there will be two fragments of mass and charge, A by 2 and Z by 2. So let us see what is the energy released in fission. We had the parent isotope, the MZA, fissioning nucleus, is splitting into two fragments of mass, Z by 2 and A by 2. And now this same thing can be written in terms of the binding energy, because the mass numbers are constant. So the difference in the masses can be written in terms of the difference in binding energy in other way around. Difference in masses of reactant minus product is equal to difference in binding energy of product minus reactant. So binding energy of the products minus binding energy of the reactant, that is the fissioning nucleus. So now we can see here, we can write this in terms of twice the volume energy term of the half the nucleus. So 2A, 2AV, A by 2 minus 2AS, A by 2 to the power 2 half minus 2AC, Z by 2 square into A by 2 to the power 1/3, and the asymmetry term minus 2AA, A by 2 minus 2 into Z by 2 square upon A by 2. So you just replace Z by 2 and A by 2 for the fission products. And for the fissioning nucleus, you have the standard formula ASAV into A plus AS into A by 2/3 plus AC Z square by A 1/3 plus AA A1 to Z. Now you can see here this volume energy term will cancel out, because it is the thing but AV 2 into AV into A by 2 means 2AV. Similarly, you can see here the asymmetry energy term will cancel out, whereas the surface energy and the Coulomb energy terms will not cancel out because they contain exponential power to the A by 2 and A. So you can write now the Q for the fission will be AS A raised to 2/3. You can take out, it will be left with 1 minus 2 to the power 1 by 3. You can see here from A by 2 to the power 2 by 3, and 2 is outside, it will become 1 by 2. 2 to the power 1 by 3. Similarly, AC z square by A raised to 1/3 you can take out, and you will be left with 1 minus 1 by 2 to the power 2 by 3. Now, if you substitute the value of the surface energy, this constant, no, 1 minus 2 to the power 1 by 3, or 1 minus 1 by 2 to the power 2 by 3, these are the values. And you can substitute the value of AS and AC. So you get minus 3.48 to the power 2/3 plus 0.22 z square by A to the power 1/3 in terms of MeV, putting the value of AS and AC. So let us see the magnitude of this surface energy term and the Coulomb energy term, and then we can discuss which term dominates for which nuclei. For 238 uranium, substituting in this value the mass number and Z, the Q fission becomes, this term will become minus 130 and the Coulomb energy term become 300. So you have 170 MeV in the predicted energy released in the nuclear fission of 238 uranium. So you can see here that the Coulomb energy term is dominating in the fission of 238 uranium. For zinc 64, Q value for fission, surface energy term minus 54.475, Coulomb energy term 49.5. So that is minus 4.9. So you can see here the Q value for fission of zinc 64 is negative, and so that explains why the light mass nuclei do not undergo fission. For the intermediate nucleus, like molybdenum 100, Q fission will be surface energy term minus 73.25 plus 83.21, that is equal to 10 points. So this molybdenum 100 fission, though it is, you can see Q value wise it is positive, but you will find that for the fission to take place, there is a barrier. If you recall, we explained that for the spontaneous fission, it has to cross a fission barrier, which is a resultant of the change in the surface energy and Coulomb energy, and the fission barrier is much higher than this Q value, and therefore the half-lives for this will be very, very high. You don't see them. So energetically it may be possible, but practically you don't see it. That explains how liquid drop model can explain the energetics of the nuclear fission process. The same thing I have tried to explain. We will discuss this more when we discuss nuclear fission, but the point I wanted to bring home is that the liquid drop model explains the spontaneous fission of heavy nuclei, wherein the competition between the surface energy and the Coulomb energy of a deforming nucleus is responsible for its fate towards the nuclear fission. So this we will discuss more in the subsequent lectures on nuclear fission. But right now we will try to summarize that the liquid drop model can explain the masses of nuclei, it can explain the beta decay energetics, it can explain the energetics of nuclear fission process. But the picture is not that good always. So there are some limitations of liquid drop model. Some of them are the unusual stability of Z and N neutron proton number having these configurations. And what I have shown here is the difference in the experimental and liquid drop predicted masses over a range of proton number and neutron number. And you will find that there are dips. That means the experimental masses are lower than the liquid drop masses at certain configurations, and they correspond to these magic numbers. So that means these magic number nuclei have lower mass than the predicted based on liquid drop. In addition to that, the ground state spin set parity of the nuclei also cannot be explained by the liquid drop model, and the existence of nuclear isomers also cannot be explained by the. There are in fact many other things which we will discuss later on. They are difficult to explain in terms of liquid drop model. So we'll discuss this all in cell model in next lecture, how cell model can take care of many of the limitations of liquid drop. I'll stop here and discuss the cell model in the next lecture. Thank you very much.